Zero-order reaction. Definition of the zero-order reaction. Explanation of the form and function of an integrated rate law. Applications of zero-order reaction. Definition of half-life time and carry out related calculations. Identification of the order of a reaction from plotting the concentration time data. Zero-order reaction. Zero-order reaction is a kinetic reaction, has independent rate of the concentration of the reactant. Which means, increasing or decreasing the concentration of the reacting species will not speed up or slow down the reaction rate. Zero-order reactions are typically found when a material that is required for the reaction to proceed, such as a surface area or a catalyst, is saturated by the reactants. As any reaction, zero-order reaction has equations, integrals, graphs, rate reaction, half-life, and other things that we will discuss it in this video. Integrated rate law. Integrated rate law. The general rate law equation is rate equal to rate constant multiplied by the concentration raised to the power n. We will take the differential form of the rate law when n equal to 0. Rate equal to negative differentiation of initial concentration over differentiation of time. After that, rearrange the equation to get differentiation of concentration is equal to negative rate constant multiplied by differentiation of time. Then we will integrate both sides of the equation. Integration of differentiation of a concentration from a 0 to a equal negative integration of rate constant multiplied by differentiation of t from 0 to t. Finally, we will solve it for AA. Concentration of AA equal to the initial concentration of AA minus rate constant multiplied by time. The integrated form of the rate law allows us to find the group of reactant at any time after the start of the reaction. Example of a zero-order reaction. The Haber process is a process used to manufacture ammonia from hydrogen and nitrogen gases. The reverse Haber process simply is the decomposition of ammonia given by the following equation. 2 molecules of ammonia gas decompose to 3 molecules of hydrogen gas and a nitrogen gas molecule. Some reactions just happen and continue at constant rate until the reactant is completely consumed. Experimental data tells us that the order of reaction, which represented by the graph below, deduce that is a zero-order reaction as rate of reaction minus differentiation A over differentiation T equal rate constant, which is applicable for only zero-order reactions. The half-life of a reaction. The half-life of a reaction T half is the time required for 1/2 of a given amount of reactant to be consumed. In each succeeding half-life, half of the remaining concentration of the reactant is consumed. Relationship between half-life and zero-order reactions. Using the integral form of the modified law, we can develop a relationship between zero-order reactions and half-life. So that the law is as follows. T half is the initial reactant concentration over 2 times rate constant, where T half is the half-life of the reaction and its unit is seconds. AA initial is the initial reactant concentration and its unit is mole per liter or molar. A is the rate constant of the reaction and its unit is molar raised to power 1 minus n, second raised to the power of -1, where n is the reaction order. For zero-order reactions, the half-life depends on the initial concentration of reactant and the rate constant. Below is a graph of time t against concentration A in a zero-order reaction. Several observations can be made. The slope of this plot is a straight line with negative slope equal to negative k. And the half-life of zero-order reaction decrease as the concentration decrease. Graph of zero-order reaction is plot of x or A minus x, which is the concentration of reactant or product, against the time t, which yields straight line with slope equal to rate constant, and intercept equal to A. If we plot rate as a function of time, we will obtain the following graph with slope equal to k or rate constant, which means that the reaction rate is completely independent of how much reactant we put in.